I believe most of the people here are from automotive domain, right? Automotive domain means we are working for the automotive system. Of course, we are not coming from automotive stream, but rather there are a lot of people coming from electrical, electronics, computer science, even chemical and mechanical engineers. So today, the agenda of the summit is role of simulation in the electrification area. Myself, I'm a hardcore IC engine guy. So currently I'm standing here and talking about electrification area. This is because I'm in this modeling and system simulation team for more than around 15 to 16 years. So I started my activity of simulation when I was in IIT Madras as a role of as a model-based system engineering for engine management system development. So then I continued my career with a lot of tools, simulation tools, and lot of course, organizations. So currently, I'm with Robert Bosch in Center of Excellence for Vehicle System Simulation. So I lead a team here using various simulation tools. So I would like to share my user stories utilizing the GT Suite tool, like how we adopt the simulation techniques for design development of EV systems and their components. And I would like to use my system because I have some key important notes here. I don't want to miss out on those. So hence, please bear with me. I will be using my laptop and also my phone to some extent. And I think thanks, Dimple. I'm here now to do my job. I'll ensure that I'll do it the best. Previously in the GT conference also, I presented about cross-domain simulation. But in this topic, I would majorly focus towards electrification area, how we use this simulation techniques. So this new business model and new mobility concepts and also the connected systems. As you know, now these electric vehicles are not dumb systems. Okay, now currently we will be driving these IC based vehicles where the energy flow is in unidirectional, right? But whereas in case of EVs, the energy flow is not unidirectional, it's bidirectional. Okay, we can also recuperate the energy back to the battery. So it means it is highly sensitive, and then also with respect to the connectivity, it's connected to the environment system. And environment system means in the sense that the traffic information, the weather information, and then also to the other vehicles also. So hence EV is a more clever system. If you see, we are adopting the technologies from the very high-end systems, like we started the simulation, and then the cruise control or the power steering, all these technologies are coming from the racing systems. And also nowadays, the technology, the AI technology, the connected solutions, all this also coming from the robotic systems, the robots. So it means that there is a huge opportunity for EV systems to still develop. So the new business models and mobility concepts, these make the system more complex, and it's a multi-domain system. Okay, and then this makes it interact, and they are tightly coupled. So there is an effect of each element or the component within each domains, like powertrain, steering, brakes, controls like this, which has an influence at a vehicle level. So hence, the system is more complex, and its development and design activity is a very tedious job, right? Like taking from this initial function development, design, integration, and then optimization, and it also requires optimization at a vehicle level. So we usually tend to optimize the product or a component only at a system level or subsystem level. So rather, in case of EV, since it is tight coupling between various domains in the component, it needs optimization and integration test at a vehicle level. So basically this demands design and development activity to be handled in a faster way. So hence virtual environment enables this. So simulation is a key enabler here, and simulation is not an alternative for the design and development activity or real vehicle testing and integration activity. So of course, simulation has certain pros and cons, but the safety critical and then time consuming and then not feasible in the real time tests can be carried out with these kind of virtual environments. So for example, in case of EV, if you have a comfort feature, okay, like driving in a traffic condition in a cold environment, okay, so here the various subdomains like the powertrain, thermal, brakes, traffic, and then the vehicle dynamics, all these are interacting. So analyzing these kind of vehicle level features is possible only at the virtual environment. Assume that if you have to do this in the real vehicle, the vehicle has to be ready for this, right? All the systems and all the subsystems, controller, everything has to be ready. So hence, this virtual environment gives you a first hand for front loading all these functionalities and features to evaluate. Yeah, coming to GT, at Bosch, we have identified Gamma Technologies GT suite as one of the tool for modeling and simulating the powertrain systems. Of course, we use a lot of tools, and I would like to make one statement here. There is no one tool in the market which can address all the aspects of the vehicle, right? Vehicle is a multi-domain system, and even of course, GT is moving towards capturing all the aspects, like moving from 3D and then also having the code simulation using Xlink, right? Yeah, every tool is moving towards that. But at this moment, there are a lot of various tools specifically for certain domains. So we use GT here for the powertrain simulation especially, and then we also integrate these tools with the other tools in the code simulation environment. So at Bosch, we have domain-specific libraries. At Bosch, we have various business units working extensively on specific components like brakes, e-axles, steering, controls like this. So we use certain model libraries built in GT suite or some other tools, okay? And then these models are well validated because since Bosch has the product ownership here, we have the data relevant to this, and then we also do this from 3D very detailed model to the very simplified models using maps or physical equations for the GT tool. So we have a list of domain models here, the controls model, PowerNet. In case of EV, it's very important to include all the domains which influence the EV operation, like the low voltage PowerNet, high voltage PowerNet, including the battery and then the chassis system and especially the thermal system. The powertrain cooling circuit, high voltage battery cooling circuit, and the HVAC systems. These are the major three cooling circuits which also influences the EV operations. So all these libraries are updated with relevant data, and of course, if you have to simulate the vehicle, one of the key aspect is or if you have to build a model, one of the key aspect is the data availability, right? Since again, OEM has specific data with respect to the vehicle, and then Tier 1 has specific data with respect to the components. So these data are not universally available and also not shareable. So hence what we do is we use the data relevant to the components, and most of the missing data we try to derive it from the test, from actually testing the vehicle or the components. So another aspect is the real road load drive profiles. So rather than using the ideal driving cycles like well-known MIDC, NEDC, WLTC, we also tend to use the real driving. We generate the real driving scenarios using the GPS information from the drivers, from the vehicle, and then we build these driving profiles using very detailed vehicle dynamics and the environment tool. And then we use the driving profiles as an input to the GT model, standalone GT model. So this also makes it modular modeling setup for covering various class of vehicles. So it's also possible to model various class of vehicles ranging from two-wheeler to four-wheeler, LCV to the trucks. And then very important is adopt credible methods for the reliable simulation. I will talk about this in the future slides. This is very important because it defines how trust your simulation results are. Of course, a lot of people have talked already about this, model-based system engineering. So model-based system engineering is an approach which is used for deriving the system architecture. For me, the system is now the virtual environment. It helps in deriving the system architecture, starting from the use case to the requirements. So this helps me systematically build the model architecture and then use the simulation. I think depending upon the use case, it can be made modular. You cannot again build a universal model for all the applications because it becomes more complex. And also, as talked in the earlier slides, the speed is also one of the important criteria, the simulation speed, I mean, right? So based on the model-based system engineering approach, we derive what system, first of all, what is your objective, what you want to achieve from the simulation, and then what subsystems, domain, element, and then functionality it should possess. So based upon this, we derive the functional and technical requirements for the modeling architecture, and then based on that, we define them. So this modular and flexible architecture helps in creating the real system which is of interest and then analyze the feature of interest. See, for example, in this, in case of EV, if your interest is to analyze the energy analysis, so the relevant components and then subsystems which are involved for the energy analysis. Say, for example, if you want to understand the how far the EV can run, okay, until the battery completely drains out with the specified battery specification, e-motor specification, and the gear ratios used in the e-axle, and then the vehicle mass. So the relevant components here are the powertrain, the brake system, and the controls, and even the environment, because you need to consider both the you just can't drive it on a slope on a flat road, right? Even the slope has a crucial input on the EV driving behavior. So these kind of features can be included when you derive the MBSE approach. Coming to the EV model building approach and simulation, of course, I think the audience here are almost following this, basically starting from the requirement phase to selection of the model. So here again, the selection of the model and the model libraries, it's greatly dependent on the what use case or what objective you want to achieve. And then of course, measured data is very important here. We can't say remotely I can do the simulation and then I can produce results and then make a decision on that. Of course, the real system has to be available. If not the real system, at least some measurement is to be provided here, because this gives some insight into the system or the components, like how really it behaves, right? I think just doing the simulation, I think also in the previous talks it is mentioned that simulation anybody can do, okay? But simulation is an artwork according to me, right? Because you should also have certain experience and certain insight of the system or the component, how actually it works under various operating conditions. So with that background, it will be very easy for you to adopt the model and then make it more credible or more trustworthy. So we use the measure data for model adaptations or parameter estimations, and then also finally to compare the simulation result to analyze how fairly my simulation results compare. So why do we do this? We have to baseline the vehicle, okay, before you do any kind of testing, right? Assume that you want to do range test with certain functionality. You designed a new vehicle function, okay, or you change the thermal system, the thermal layout, or you want to change the battery capacity. So for that, before you have to baseline a vehicle, you have to make sure that my model is able to capture all the steady state and dynamics behavior of the system, and then you go on to making this retrofit or the data fitment and then do the delta changes and then analyze and quickly estimate what is the uniqueness your component or new function is going to give, and then able to release it. So once the baseline model has been validated, so then we go on doing the test of how the performance of the EV vehicle. I think this is a very common simulation cycles which we use, as I said, MIDC, WLTC, and also this is one of the real driving cycle which we ran for around 3 hours, around 180 kilometers, yeah, to understand what is the real range the vehicle gives with these kind of driving profiles. So we took 100% SOC and then we drained the SOC in order to see how much range we could get, and then also the simulation gives an insight to you what is the recuperation potential. See, for example, in this plot you can see there in there that 23%, 24%, 26%. You can see how the variations happens with the driving patterns, how much energy is potentially available for recuperation, and then also the overall energy consumptions with the different driving cycles. So it shows that how sensitive the EV system is for the driving patterns. And then we also did some thermal analysis of various components. With this we also derived what are the energy losses happening at various components, okay, and then how we could optimize them. So this was also one of the study which carried out, and this is very important. We can see that this is the plot of energy consumption versus different constant vehicle speeds. As we know, EV is very sensitive to vehicle speed. As the speed increases, the losses increases, and then the energy consumption is very high. So this also gives you an insight how we can optimize the utilization of the EV, and then also give an upfront, you can also design certain features like giving in information to the driver, hey, you are going on a non-optimal driving speed, you try to reduce or you try to control. Usually it is well known that 70 to 80 kilometers per hour is the best suitable speed for the EV operations. Okay, and then also you can see in this plot how is the impact of the gradient. Gradient is one of the worst enemies for the EV vehicle. It's like increasing significantly with grade. You can compare with the flat road with a 5% gradient, 10% gradient, how it is influencing. And then also the influence of the accessory powers. Like for example, there you can see the high voltage power net, like the AC compressor influence at various speeds, how it is influencing the power consumption from the high voltage battery. So some plots here, again as I mentioned, various maneuvers. So these maneuvers are carried out on the real vehicle. So for this, we took a electric vehicle. We put the vehicle on the chassis dyno. We conducted all these maneuvers. We recorded the data, and then we used these as a baseline for comparing the simulation results. You can see here, now we have a plot of e-machine torque, and then the wheel energy consumption, and then the overall high voltage battery consumptions. So once we baseline this vehicle, and then we go to the next important topic of virtual retrofitting. This is very important in defining what certain specific components can do to an EV vehicle at a system level. System level means our focus here is on the range, right? In case of EV, it's range. I think until now we are talking how much in case of ICE. So now it's going to change. We are going to ask about how long. And the next question is how safe. As several people talked about batteries catching fire, okay, we can also analyze the thermal derating influences on the high voltage battery and also on the powertrain components. So we do the baseline vehicle model initially validated for the energy flow, powertrain and chassis components, and then we retrofit the competitive components in terms of data, and then evaluate the performance improvement and range benefits achievable with the competitive components, and then we do the potential benefit analysis for the predictive functions like eco maneuver. So eco maneuver uses basically the horizon information and then optimally controls the vehicle speed rather than allowing the driver to drive on his own way. And then also some optimizing the thermal components. We have predictive control functions for the thermal system. So this is also possible to quickly evaluate. Some plots again here to show how the influence of various components with the different efficiency maps and then the losses fare between each other at a system level. You can see here with the e-drive system A and e-drive system B, of course, there is a difference there because with respect to the speed also and the energy consumption, because we use optimal gear ratio. Gear ratio also has been changed. So hence the power losses as an influence, and then finally the energy consumption from the battery. So we see that difference between e-axle A and e-axle B, how it's varying at a system level, and then finally influencing the range on the EV at different driving cycles, standard driving cycles and also the real driving cycles. And another important aspect is it could also be utilized for designing and selecting your brake components. As we know, at Bosch we have various braking components like ESP, iBooster, and then IPB, integrated power booster, which basically enhances the recuperation potential. Hello? Yeah. So as we go with the higher advanced braking components, it is possible to recuperate more, like 0.1G to 0.2 and 0.3G. So this also helps in the simulation, at system level simulation, helps in deriving, if I change my component, if I go for higher deceleration capabilities, what is the influence on the range? So we can clearly see that at different driving scenarios, how it is going to influence. And then when we combine the different e-axles with the optimal losses and then the higher recuperation potential, we see that clearly already around more than 10% there is an improvement in the range. So hence, simulation helps in deriving these kind of uniqueness in the different components. and then it is possible to model various subsystem domains in GT suite, and then also handling the data exchange. When I say about the retrofitting, the data exchange is also possible using the GTOs by component switching. Real test cycle measurements we compared, as I showed, and the simulation results show improvement in the HV battery energy consumption with comparative components and effect on EV range. So it means we have tried to include all the aspects of the vehicle, like the traffic, powertrain, and then the driving pattern also, using the driver and environment simulations. So with advanced braking components having higher deceleration capabilities, it results in more energy recuperated overall effect on the EV range. So apart from this, we also carry out simulation. This GT powertrain model helps us in deriving the loads, real loads, using the real driving profiles, coming to the HV battery, and then hence design the HV battery and also predict the life of the HV battery. So we use a different model for the high voltage battery. It's a very detailed model, electrochemical model, using AIML techniques also, augmenting AIML techniques also. So for those, we use these data. I think another talk was talking about the data availability, right? This is also crucial. So of course, the data available for years together for estimating the battery age is unimaginable. So using this simulation techniques, it is possible to generate huge amount of data. Of course, this data has to be reliable. We have to check on that one. So using this reliable data, it is possible to derive the high voltage battery features. So with that, I would also like to make one quote from a professor from IIT Guwahati, Dr. Praveen Kumar. So indigenous technology and domestic expertise and jugaad mentality are some of the problems restricting the EVs, so getting popular. I feel that definitely this has to be very critically considered, and then designing and understanding the local regions, environment, temperature, and designing a component, especially in case of EVs, is very critical, and then simulation plays a crucial role in this. Thank you all.